Okay, in this lesson, we're going to talk about the principles of mathematics. Okay, these principles, as we are going to go through them, you will find that they are all self-evident facts. They are all self-evident facts. So I'm going to write here as self-evident facts about numbers. The first one, any number times 1 stay the same. Okay, using words, that's how we say it. In mathematical notation, we say A represent any number times 1 multiplied by 1 is the same as, equal sign meaning is the same as the number we started with. So any number times 1 stay the same. So this is called a statement. And of course, you can also write it as A times 1. You don't have to write the dot, right? And we usually don't write it this way because this cross may be confused with X, right? So you can also leave a space there in between. That's fine too. And in most of cases, we just write this statement as we speak it. The meaning of it is that any number times 1 stay the same, okay? So we're going to use the first form. So what are the cases we have used this principle? Okay, you have definitively used this principle before. For example, look at the first example here. Example number 1, right? One of the cases is when we reduce a fraction, right? Suppose we reduce a fraction. Suppose we have a fraction. Okay, this fraction is 5/10. And we know this can be reduced, right? And 5 is the same as 5 times 1. 10 is the same as 5 times 2. And with that, we have 5 divided by 5. 5/5 is 1. So we have a situation which is 5/5 multiply 1/2. 5/5 is 1. So any number times 1, half times 1 is the same as, right? So same as. So that equals to 1/2. Okay. Another situation that we use this property is that when we try to find common denominator. For example, we have 1/2 plus 1/3. Yeah, we don't have the same denominator, right? We have identified the common denominator, which will be 6, right? So 1/2 plus 1/3. And we want to convert them to the same denominator. And we realize the common denominator we can use, LCD, the least common denominator will be 6. So we try to, right? So we will try to do something, right? We'll try to do something here to make it a new denominator, right? The new denominator will be the common denominator. So we're going to have something over 6 plus something over 6. Along the way, we want to keep them to be of the same value, right? So what can we do? We're going to apply this property, right? So I'm going to multiply by 1. I'm going to multiply by 1 here. But we're going to compose the 1 in such a way, okay? We're going to compose the 1 in such a way that this first one we're going to choose it to be 3/3. And the other one, we're going to choose it to be 2/2. This way we will get the common, we'll have the same denominator. So the first part we get 3/6. 1 times 3, 2 times 3 is 6, 1 times 3 is 3. And on this part, 3 times 2 is 6, 1 times 2 is 2. So now we have the same denominator. We can add the numerator, which is 3 plus 2 over, we keep the same denominator. So in the end, we get 5/6, right? I'm sure that every one of you probably have done this before. Otherwise, you're going to have a hard time in pre-calculus, okay? Now, the third example I like to give you when this principle is used is rationalization, okay? So the first case, we reduce fraction. The second case, we're going to use this to make a common denominator, right? Make common denominator, right? This principle, any number times 1 stay the same. The third example I like to talk about here is rationalization. Okay, rationalization. Rationalization, it could be of the numerator, rationalization of the numerator, or denominator. Okay, so we're going to first talk about the rationalization of the denominator, which you probably have seen before. Okay, you probably have seen before. Okay, example. Okay, so first of all, what is rationalizing the denominator? Okay, for example, I have 1 over square root of 2. Because our objective is rationalize the denominator. And right now we have a radical in the denominator. And we want to get rid of the radical in the denominator. Okay, so in order to achieve that goal, okay, and we're going to use the property of any number times 1 stay the same. So we're going to use this property. And we're going to choose our 1 in such a way, right? So we're going to rationalize it. We're going to get rid of the radical, right? 1 over square root of 2. And we multiply by 1. We know anything multiplied by 1 stay the same. But how do we choose the 1 though? We're going to choose 1 to be square root of 2 over square root of 2. And we know this is going to be 1. So the choice of 1 is really chosen based on the situation we're in. Now, after this choice, right, and we can maintain the equal sign because this number is the same as the next number, which is we merely just multiply by 1, and we continue this process. The denominator multiply denominator, right? So square root of 2 multiply square root of 2, sorry. Okay, the square root of 2 multiply square root of 2. And the numerator is 1 times square root of 2, that's a square root of 2. Square root of 2 times square root of 2, that's going to be square root of 4. That's square root of 4. And square root of 4 is equals to 2. So we have square root of 2 over 2. The final answer we have here no longer has the radicals in it. So this process of converting a fraction with radicals in the denominator to another number, which is the same as the original number in value, but in the denominator, we don't no longer have the radicals. This process is called the rationalization of the denominator. And the rationalization of a numerator will be similar. And for example, right, rationalization of numerator, rationalization of numerator. Rationalization of numerator, for example. Okay, for example, suppose I have root 2, right, over 3. I want to rationalize the numerator. What would I do? Right? We will do something similar. We still multiply by 1, but we need to know what is our goal. Our goal is to get rid of the radicals in the numerator. The radicals in the numerator is root 2. So we know that if we multiply another root 2 over root 2, which is it's 1 here, it doesn't change the value, and we will be able to get rid of the radicals in the numerator. Now you may wonder, do we have a situation that we're going to do that? Well, yes, you will. Okay, of course, these are simple examples. There will be more examples coming in in the semester. So this is the first mathematical principles of that any number times 1 stay the same. The second principle. Okay, so we call it principle number 2. This principle says any number as 0 stays the same. Any number as 0 stay the same. Okay, so suppose we use A represent any number, add a 0, stay the same. So this is the second principle. And you see, such a self-evident fact, when do we get to use it? Yes, we absolutely use it. We absolutely use it. Okay, so example. Example, in this case, for example, we want to do complete a square. Completing a square. Okay, for example, we have an expression which is x squared plus 2x plus 2x. And we want to make it something like, we'll have a perfect square plus something else. Plus something else. Okay. In this situation, if that's the goal, right? This is our goal. Okay. That's what we want to get to. What do we do? In the final expression, we have a part which is a perfect square. How do we get to it? Okay. I'm just going to give you the process. Some of you may know how to do this, or some of you may not, but we will have other opportunities in the future to go over this. And I will tell you where, you know, there's a reading about this, and this is the contents of, you know, intermediate algebra class. Okay, and we will, you know, we will review this part in the future. So here, what I will do is that I'm going to add a 0. I'm going to add a 0. We know that's not going to change anything. But I'm going to choose the 0 in such a way I will make the perfect square, but still keep the balance, still keep the equal sign validated. Okay, and how I'm going to choose this number? Okay, this number I choose here is going to be 1 squared. You know, 1 squared is still 1. It's the same as 1. 1 squared minus 1 squared. I'm adding a 0, so stay the same, right? The latter expression is the same as the original. But these 3 will make a perfect square. Will make a perfect square because, note, when we have x plus 1 squared, and that equals to x squared, we FOIL this, right? Plus 2x plus 1, or 1 squared. So with this statement, we know this statement is true, right? Then these 3 is exactly, you can remove 1 squared, it just doesn't make any difference, right? So this is going to be x plus 1 squared. So these 3 make the perfect square. So on this question mark plus a question mark here, we're going to have a plus of -1. Okay, of course, you can just write -1. Okay, remove the plus sign. So we transform using this principle. Any number adds 0 stay the same. We transform a function from one form, or an expression, we transform one expression to another. Okay, in the new expression, it gave us more insight, So this is something we are going to have further examples in the future. Okay, so this illustrates the second principle. Okay, throughout the semester, we will be actually addressing these principles throughout the semester whenever we use them. Now, we have gone over 2 mathematical principles. Principle number 3. Okay, if one number is the same as the other, there's an if statement, right? You see in the previous 2 principles, there's no if statement. Okay, the first 2 principles are true forever. It's true for any number. Okay, no attachment, no restrictions. But in the 3rd principle, we have an if statement. If one number is the same as the other, then we're adding the same number on both sides. So we add a number c on one side, and we add number c on the other side, the same number. We're adding the same number on both sides. They will still be the same. Have you heard about this statement? I'm sure you guys have learned about the application of this statement. For example, right? Example number 1. Right? You definitely have used this. For example, suppose we ask you to solve for x. Right? Solve for x. This is equation solving, but what is equation? Equation basically says, say, I'm going to give you an example, okay? 3x minus 6 equals to 9. What does this mean? This is basically says if, okay, so the meaning is if, right? The meaning is when we ask to solve for something, the meaning is there's an if statement embedded. There's an if statement embedded. It basically says if A is the same as B. If A is the same as B, but what is A? 3x minus 6 is A. What is B? B is 9. Then, right? If 3x minus 6 is 9, then what is x? What is x? So first we make sure we understand the meaning. We understand the meaning, right? So when you're given a question, if solve for x, it basically gives you a if statement setting. It says if this is true, right? We'll have other interpretations in the future, but first we need to understand the meaning. So we are in the if statement setting. So in this case, we can do what? We can do something about it because our goal is to isolate x. I trust every one of you know how to do this, right? So we're gonna add 6 on both sides. Minus 6 equals to 9. So we're gonna add 6 on both sides. So if this is true, then this is true. So I want you guys to hear the logical connection. I know every one of you know how to do this. I do. Okay, but I want you to understand that how to read this. Okay, how do you read the mathematics in your textbook or on the screen or on the blackboard, on the whiteboard, whatever. So this first sentence means if, and then, right? So typically those words were not written there because for shorthand notation, but we need to understand, okay? So after this, we end up with what? 3x equals to 15. And I know you're gonna go further. You're gonna go further, right? I'm sure you can go further. But I'm gonna stop here. I'm gonna stop here because I'm gonna address principle number 4. Principle number 4 says if A is the same as B, then A times C is the same as B times C. But here we have a very, very important attachment requirement, provided that C cannot be 0. C cannot be 0. So this whole of it is principle number 4. Okay, we're going to explain the importance that C cannot be 0 just in a minute. So now let's complete the question we had in exercise 1, right? So EX2, example number 1, continued. Okay, so if 3x is 15, right? If 3x is 15, then what can we do? We can apply principle number 4, which is multiply on both sides the same non-zero number on both sides. Okay, you can also say, oh, I'm going to divide both sides by non-zero number. That's okay too. Okay, that's okay too. So there's 2 ways to say this, right? You can say, hey, I'm going to divide both sides by 3. You get your answer. You can also say, hey, I'm going to multiply both sides by what? By 1/3. Either way is fine. They're both reflections of the same principle. Okay, so in the end, we get x equals to what? 5. Okay, or if you prefer, you say, oh, I'm just used to, the way I do it. I'm just going to divide both sides by 3. No difference. No difference. Okay, you multiply or divide both sides by 3. They're all the same. They're all the same. Okay, so in the end, we get x equals to 5. Okay, all right. Now, why this requirement? Why? Why this requirement? Why this requirement in principle number 4? Why? Okay. If this requirement is removed from principle number 4, then principle number 4 will have to be thrown to the trash. That's how important this is. Okay, so pretend, okay, suppose we don't have that. Suppose we remove this condition. Okay, that C cannot be 0 is removed. What will happen? What will happen? Okay, so I'm going to show you disaster will happen. Terrible things will happen. The entire mathematics, as you know of. Okay, if this is a building, right? 25-story high or 100-story high, is going to collapse. And I'm not exaggerating. I'm not exaggerating. Okay, so let me show you how. Let me show you why. Okay, so this condition is absolutely, absolutely important. If you remove it, we don't have principle number 4. Principle number 4 is garbage. All right, so suppose we remove it, what will happen, right? So let me show you. So if, right, so I'm going to start with the same context. If A is the same as B, right? If this is true, then I can say A times A is B times B because they're the same number, right? And we can also make up all kinds of stories, A times B, right? Because A is B, B is A, right? So we will end up with something like this. Then we will have A squared equals to B squared, right? And we have A that will also equals to A times B, right? So if A equals to B, if A is the same as B, then this will be true. Then this will be true, right? And what is more, because they're the same number, right? So I can say, hey, A squared minus B squared is going to be the same as A squared minus A times B, right? Because they're the same after all. A squared minus B squared is going to be 0. A squared minus AB is going to be 0, right? All right. Right, so I can say then. Right, I can say then. And then I'm going to factor both sides. I'm going to factor both sides. Okay, if I factor A squared minus B squared, the factored form will be A plus B multiply A minus B equals to, on this side, on the right-hand side, we're going to factor out the A. So we're going to get A minus B, right? Now, you can verify that A plus B times A minus B is indeed A squared minus B squared, right? If you need help, let me know. Now, we have A minus B on both sides, A minus B on both sides. So I'm going to use that principle, right? I'm going to use that principle. I'm going to divide A minus B on both sides. Then what do I get? I will get A plus B equals to A. Or like some of you would say, hey, I'm going to cross them out, right? Reduced, cross them out, right? You have A minus B on one side, A minus B on one side. I'm just going to divide both sides by A minus B. Reduced, whatever you say. Then what? Because A is the same as B, and B is A is B. Therefore, A plus B is the same as A. We can write it as A plus A equals to A. Right? Because B is the same as A. Then what do I get? Then I will get 2 times A is A. And then I can cross out the A. What do I get? I get 2 equals to 1. At this rate, I can get 1 equals to 2. Then I can get 2 equals to 3, right? 3 equals to 4, 4 equals to 5, and so on and so forth. You can keep going. And what does that tell us? It tells us 1 is the same as 2. That's ridiculous, right? So this is entirely false. Which step that caused this falsehood? Which step has caused the falsehood? I want you guys to, when you watch this program at this time, I want you to just pause this for a moment. Okay, pause the program for as long as you want and try to answer. Try to go back, try to examine the steps, and try to answer the question why. Because I'm going to give you the answer. I'm going to give the answer. So which step has caused this fatal falsehood, which could cause the collapse of the entire mathematics? Okay, so here's the answer. Okay, the problem is this step. From this step to the next one. Okay, so from this step to the next one. When we cross out the A minus B, we know that A is the same as B. So when you do A minus B, you're dividing by 0. We're dividing both sides by 0. So when we divide both sides by 0, it causes this fatal falsehood. This is the reason why we have to maintain this condition in principle number 4. Okay. This is why we have to maintain this condition. So this condition is absolutely critical. Absolutely critical. Okay, so now, we understand why principle number 4 has to have that condition attached to it. C cannot be 0. So whenever we have an if statement, A equals to B, if A is same as B, when you multiply or divide, we can never ever multiply or divide by 0. That's very, very, very important. Okay, so that's principle number 4, sorry. Now, we have 2 more to go. Okay, principle number 5, sorry. Principle number 5. Okay, so we're gonna first use words, okay? Because the reason I'm using words, I want you guys to think about it. Okay? So when we look at the mathematical principle, when we look at the mathematical symbols, we have to think about the words. So when we use the words to make sure we understand. Okay, so now if statement again, if the product, a product of 2 numbers is 0. Okay, if and only if one of them is 0. In your previous experience, you might have learned the statement slightly differently. But here I introduced a statement called if and only if. If and only if. So this is like, it's actually 2 statements. All right. If and only if, right? It's a 2-way street. It's actually into 2 statements. One statement says, if a product of 2 number is 0, then one of them is 0. The second statement is basically saying, if one of 2 number is 0, one of two numbers is 0, then the product is 0. Okay, so that's the if and only if. So on the first if statement here is basically saying, if you look at the street, right, from left to right, okay, it's from left to right. On the other one is from right to left. From right to left. When we do from right to left, when we do from right to left, then we get the next statement. So when we have if and only if, it's like a 2-way street. 2-way street. You can go from if left, then right. Or if right, then left. So it's a 2-way street. Okay. Now, if a product of 2 numbers is 0, then one of them is 0, right? In words, we basically say, that's what we say. In mathematical expression, we say A times B is 0, right? So if, then A is 0, one of them is 0, right? A is 0 or B is 0. Here, I want you guys to notice that I have or here, because we don't need both of them to be 0 in order to get a product equals 0. As long as one of them is 0, then that's fine. So this word or has to be or. If you use and instead, it will be a mistake. You guys with me? Okay, for this, I want you guys to look at, we're gonna have a recording, there will be a recording for truth table. So refer to truth table. Okay, which will be another session, which will be another session. For now, I want you to make sure that you use or. Now, let's look at the other side of the statement. If one of two number is 0, right? Then of course the product is going to be 0. That's pretty obvious. Okay? So this is the principle number 5. Principle number 5 is the kind of two-way street. Okay? Now, last one. Principle number 6. Principle number 6. What is principle number 6? Principle number 6 actually is very interesting. You know it already. Okay, I'm just reviewing it here. Okay. When we multiply a positive number with another positive number, a positive number times a positive number, what do we get? What do we get? We get another positive number, right? So positive number multiply positive number is a positive number. A positive number divided by a positive number it's also going to be a positive number, right? What else? A positive number, right? A positive number multiply a negative number, we will get a negative number. A negative number multiply a positive number, we're going to get what? A negative number. Okay. And next, for division, it's the same thing. Let's finish up the negative. Negative times negative, what do we get? We get positive, yes. Okay. Now let's look at division. Okay. If we have a positive number divided by a negative number, right? We have all these cases, right? A positive number divided by a negative number. It's going to be a negative number, yes. A negative number divided by a positive number is going to be negative. So this is too easy for you, right? How about a negative number divided by a negative number? Yes, it's going to be negative or positive. Negative divided by negative is positive. Yes, I hear you. Okay, so this is principle number 6. All of these together is principle number 6. Do we agree they are self-evident facts? Yes, they are. Okay, throughout this semester, we're going to see how these principles that are going to be guiding our steps, that has been guiding our steps in the mathematics you have learned before. You may or may not be aware of them, but I will work hard to make sure you have awareness of all of these principles. And you will see how these principles will be used throughout your preparation for calculus class. Okay. And that's all for this lecture.